Hey everyone, this is Connor Mead with the Calculation Center again, here with another video in our calculus series. In this video we'll be going over some more differentiation basics, and this one we're going to be covering the properties of the derivative, or some kind of rules that tell us how to combine the results of our previous video into differentiating more complicated functions. Now, we'll go over these one by one with a couple of examples for each of them. They're differing difficulty to apply, I would say. We're going to start with the simplest one, which is linearity. Okay, this is a property often referenced in maths, but essentially whatever it means in this case is just that we can essentially move constants outside of the derivative for free, and we can also split up derivatives for free. Okay, so in this as it says dcf dx is just c df dx, and d of f plus g dx is df dx plus dg dx. So here I've got an example down here. F of x is equal to minus x cubed plus 5x plus sine x. Now we're going to use this rule of linearity to, and the results we got from the previous video to evaluate this more complicated function. So therefore, df dx is equal to, well, we can first of all split it up like this. It's equal to the derivative of minus x cubed dx plus the derivative of 5x dx plus the derivative of sine x dx. This is from the second property that says we can split up derivatives over sums. And this one, we're going to use the linearity property here to say this is equal to minus the derivative of x cubed dx plus 5 times the derivative of x dx plus the derivative of, well, we know this immediately, this is cosine of x. But now we also know the derivative of x cubed dx and the derivative of x dx. So this is going to give us minus 3x squared. The derivative of x dx is just 5. So this is our answer. And I've only written down one of these because it's simple. The idea is just that you can differentiate each part of your function kind of independently, as long as you understand parts to mean different terms you're summing over, and also that you're allowed to bring constants out in front. Okay. Next up is probably the most complicated rule, I would say, and that's the chain rule. The chain rule deals with compositions of functions. So here we have h of x is equal to f of g of x. That means, first of all, we get an input x, we do g to it, and then we do f to g of x, okay? That's a little complicated to think of, but it's easier to see in example. And the rule is, associated to composition, is if h is a composition of the functions f and g, then dh dx is equal to dh dg dg dx. Now, dh dg might seem a bit ambiguous right now, but I think it's going to be, this is a convenient way of writing it, and with a little care we can understand this to be what this means, and we can use the notation to help us remember some rules. Okay? A little more formally, dh dg we're interpreting as df of g of x dg of x, which is going to be equal to d f dx, except we're evaluating it at g of x. That's properly what we mean, and you've probably seen it written as this before, but I recommend thinking about it like this. Okay? So for example here, h of x is equal to e to the 3x, so we need to identify f and g here. So in this case, first of all we triple x, and then we exponentiate it, we raise it to e to the power of 3x. So in this case, g of x is equal to 3x, and f of x is equal to e to the x. And what we know by the chain rule is dh of x, dh dx, is equal to the derivative of h dg. So let's just write that out. E to the 3x, g of x is 3x, and we multiply it by dg dx, which is the derivative of 3x dx. Okay? And basically all you do for this is you imagine 3x is another variable, so we call this u, and then this is the derivative of e to the u du. And we know precisely what that is. That's just e to the u, but u is equal to 3x, so this becomes just e to the 3x. And similarly, the derivative of 3x dx, we can move the 3 out in front by linearity. So this just becomes 3 times dx dx, which is just 3. Okay? So that's just a simple application of the chain rule. Now this is a little more interesting perhaps. H of x is equal to 2 plus x cubed all to the 20. Now, theoretically, this is just a polynomial, so it's very easy to differentiate. However, we'd have to expand out this power of the 20. Like, this would have to be a complicated thing to expand, certainly impossible to do by hand in an exam situation. So how do we do this? So the derivative of h dx is equal to, well, let's split this up again. In this case, g of x is the thing we do first. So this is equal to 2 plus x cubed. And then what we do afterwards is we raise it all to the power of 20. So f of x is equal to x to the 20. So therefore our derivative is given by d of 2 plus x cubed to the 20, d 2 plus x cubed. I'm just going to get rid of this now momentarily so we can, or I can put it over here perhaps. And then we have to multiply this by the derivative of 2 plus x cubed dx. So this term to the right, this comes out to be 3x squared. By the linearity again, we split this up, d2 dx is equal to 0, dx cubed dx is equal to 3x squared. And this term here is equal to 2, oh, well, actually, let's be a little more careful. So how do we differentiate? If this was u to the 20 du, this would be 20u to the 19. So that means it's 20. In our case, u is equal to 2 plus x cubed. So it's 20 times 2 plus x cubed. I'm just going to get rid of this because it really is taking up too much space. Times 9 to the power of 19, right? Because if this was du to the power of 20 du, then we'd get out 20 times u to the power of 19. Okay? So just tidying it up a little bit. This becomes 60 x squared times 2 plus x cubed to the 19. And this is still very messy to expand and everything, and would be difficult to do, but this is the correct answer. Okay? And lastly, our question is for h of x is equal to sine of x squared. Here, of course, g is equal to x squared, f is equal to sine of x. So dh dx is equal to the derivative of sine of x squared dx squared. Let's get rid of this again. D of x squared dx. Okay? And again, remember that dh dx, if we just wrote this out naively, this would look like d sine of x squared dx. So we can kind of imagine these dx squareds cancelling to get us back to our original position. But evaluating this like before, sine of u du is of course cosine of u, so this is cosine of x squared, and this is just 2x. Let's get rid of this as well for tidiness sake. So it's cosine of x squared times 2x, or the more normal way to write it might be like this. Okay. We'll go over the next two properties of the product rule and the quotient rule in the next video, but hopefully this has been helpful in clearing up the linearity and chain rule properties of the derivative.